let's have a look. Question 5, start on a new page. Make sure to start on a new page. The reaction of 15 grams of an impure sample of calcium carbonate, CaCO3, with excess hydrochloric acid, HCl. Okay, so just take note of these important words. We'll come back to discuss them in a bit. The reaction of 15 grams impure sample of calcium carbonate. Okay, impure is important. Okay, because if it's impure, not all of it is going to react. Okay, the way you can think of impure is that there's a compound that has some dirt in it. Okay, so if it has some dirt in it, then the dirt is not going to react. What's actually calcium carbonate in it is going to react. So in this case, there's 15 grams of the impure sample of calcium carbonate. Perhaps only 11.5 grams is actually calcium carbonate, and then the 3.5 grams, or 3.5 grams is dirt, let's just say. Okay, obviously these are not the exact values. I'm just talking here, just for an example. Okay, so very important is the impure sample. Then we talk about excess hydrochloric acid. So remember, the thing with excess, when they tell you it's excess, like they say, okay, this is excess, right? We have excess of this. It just means that okay, if we think of it as pizzas, okay, yeah, pizzas, yep. And just say to make one pizza, we need 10 pepperoni. Okay. Now, let's just say we have 153 pepperoni. And we have 15 pizza bases. So in this particular case, obviously, we have 15 pizza bases and 153 pepperoni. We can make 15 pizzas. Definitely. Okay. However, we're going to have 3 extra pepperoni slices or whatever, because we have 153. We're going to use up 150 to make up 15 pizzas, okay? But we're going to have 3 extra pepperoni. So that is essentially what excess is, people, okay? It's okay, you have a certain amount of CaCO3 and you have a certain amount of HCl. And remember, these are chemical reactions, okay? So there's a certain amount of CaCO3 that reacts with a certain amount of HCl according to this molar ratio, according to how they react, okay? However, in this particular case, the amount of HCl that's in this reaction is actually too much. So we'll use up all the CaCO3 and just say we mix them with HCl and CaCO3, and there's not a perfect amount of each where they will both just finish up, okay? There's extra HCl, okay? And that's basically what excess is. At the end of the reaction, we are left over with a certain amount of HCl. Okay, so the important part here is not all of it reacts. So if they tell you that there's 15 grams, okay, let's use a different number. If they tell us that there's 14 moles of HCl, we can't use that 14 moles to do any calculations, okay, because the HCl is in excess. So not all 14 moles are going to react. When we do calculations, irrespective of the topic, okay, even in acids and bases, even when we're dealing with limiting reagent and stuff, the only amounts that we can use the molar ratio for are the actual amounts used and the actual amounts formed. This 14 moles is not an actual amount that is used. This is just an example. It's not actually the correct amount. This is a correct amount, however, the 15 grams of impure sample of calcium carbonate, We need to note that this 15 grams we also can't use in the molar ratio. Why? Because not all 15 grams of this impure sample of calcium carbonate is going to react. Only the part that's actually calcium carbonate is going to react, and that we're probably going to have to calculate. Okay, so just keep that in mind. Okay, so two very important pieces of information, both of these informations we cannot use in the you cannot use the molar ratio right now, because again, impure sample, not all of it reacts. Some of it is impure, some of it is dirt. Excess hydrochloric acid, not all of it reacts. Some is going to be left over in the end. So both of these amounts we can't use now right now to do any calculations. Okay, cool. They say, okay, so the excess HCl of concentration 1 mole per decimeter is used to investigate the rate of reaction. The balanced equation for the reaction is CaCO3 plus 2HCl gives us CaCl plus H2O plus CO2. The volume of CO2 produced is measured at regular intervals. A sketch graph representing the total volume of carbon dioxide gas produced as a function of time is shown below. Okay, cool. So we have this graph, right? It's the volume of CO2 being produced. So tell me, is this a product graph or a reactant graph? Is this a product graph or is this a reactant graph? What kind of graph is this? Yeah, this whole time my screen has been paused. No one told me. Just talking about the pizzas here. And here we go. Okay, does anyone know what type of graph this is or no? Can I get a yes or a no? Harry Kane? Sorry about the Bundesliga, by the way. Xabi Alonso came in and stole your dream of winning a trophy after all these years. Okay, we don't know. Thank you for letting me know. So firstly, they say, let's use the color orange, because why not? The volume of CO2 produced. This means it's certainly a product. So this is a product graph. Okay, and we can also see that we start at 0 and then we end up with a certain amount. That shows that production. Okay, remember the graphs? If you can load, this would be nice. Instead of us looking at blank papers. There we go. So remember the graphs, okay? Starting from nothing and ending up with something at the end, that's product. Reactant is starting off with a high amount and then decreasing until the end, where we either have 0 or we have a much less amount. That's reactant, because you use up reactants to form products. Okay, so yes, product graph, and we can see that CO2 is on the products end, so it's again product graph. So they say the volume of CO2 produced is measured at regular intervals. A sketch graph representing the total volume of carbon dioxide gas produced as a function of time is shown below. Perfect. 5.1, define the term reaction rate. Define the term reaction rate. So reaction rate, you can use many different definitions. The main one is a change in concentration of products or reactants per unit time. That's the main definition. You can also use change in amount or number of moles or volume or mass of products or reactants per unit time, or the amount or the number of moles, volume, or mass of products formed or reactants used per unit time, or you can use rate of change in concentration, amount of moles, number of moles / volume / mass. I'll put those definitions in. 5.2, give a reason why the gradient of the graph decreases between T2 and T3. Give a reason why the gradient of the graph decreases between T2 and T3. Anyone want to give me an answer? Do we know the answer or what to say? If you don't know, you can just say no or attempt to give me the answer. So please, we must remember about this gradient story, right? That's why I went through it. We need to be able to understand when so we know for these first two examples, right? The y-axis is increasing. As we move to the right, the y-axis value is increasing. And for the second two examples, as we move from left to right, okay, the y-axis value is decreasing. But we need to be able to understand the gradient story, okay, whether the gradient is increasing or the gradient is decreasing. So looking back at these two graphs, okay, that's why I drew the tangent lines, the straight line tangents, because then we can see whether it's becoming steeper or whether it's becoming less steep. Okay, so in this particular case, on the left, we have an increasing gradient because have a look at these straight lines as we go along. They are becoming more and more steep. 1, 2, 3. More and more steep, which means an increasing gradient, which means an increasing rate of reaction. Let's look at these. Even though the y-axis value is still increasing, but the gradient, the rate at which the y-axis value is increasing is slowing down a little bit, right? So we can see that from the gradient lines becoming less and less steep, indicating gradient is becoming less and less steep. Let's look at this one. Gradient becoming less and less steep, decreasing gradient, decreasing rate of reaction. And remember that the gradient in this section, if we're dealing with a reactant or a product, okay, represents rate of reaction. And you can see in this particular instance, the gradient becomes steeper and steeper, which means an increasing gradient, which means an increasing rate of reaction. So now, let's have a look here again and give a reason why the gradient of the graph decreases between T2 and T1. Sorry, T2 and T3. So we can confirm that by drawing tangent lines becoming less and less steep. Becoming less and less steep. Becoming more and more like flattened out. So definitely we know that the gradient of the graph is decreasing. Can anyone give me a reason? I can still hear you guys. So I can still read the chat. Can anyone give me a reason why the gradient of the graph decreases between T2 and T3? Okay, I'll take that as a no. I don't know why this light is so creating that thingy. Okay, so the gradient of the graph is decreasing here because the rate of the reaction is decreasing. Okay, because gradient represents rate of reaction and the rate of the reaction is decreasing from T2 to T3. Okay, what we can also understand is, okay, remember as this reaction is taking place, the reactants are being used up. The reactants are being used up to form products. So now when we start off the reaction, we have a lot of reactants. When we start off the reaction, we have a lot of reactants and we use up and we use up and use up and we consider towards the end. This is towards the end of the reaction. Now towards the end of the reaction, we have much less products because we've used up a lot of them. Okay, so towards the end of the reaction, we have much less products. So the much less reactants. So the concentration of these reactants have decreased. Remember, when we have a lower concentration, it results in a slower rate. So because we've used up most of the reactants towards the end of the reaction, we have a low concentration of the reactants, and therefore, sometimes the rate of the reaction slows down towards the end of the reaction. Okay, so that's the reason that we can give for that. The rate of the reaction decreases, the concentration of HCl and CO3, CaCO3 is decreasing, okay, or the concentration of the reactants decrease, reactants are being used up, you know, that's the type of answer that we can give for that one. Again, I'll leave the memo answer for you there. 5.3, changes in the graph between T1 and T2 are due to temperature changes within the reaction. So between T1 and T2, they are telling us it's due to temperature changes. Can someone help me? Can you comment on the gradient of the graph between T1 and T2? Is the gradient increasing or decreasing? What does it look like? Someone tell me. Someone help me out. Please and thanks. Gradient of the graph is increasing. Excellent. Excellent, right? So gradient of the graph is increasing. Very good. We can see that because the graph is becoming steeper. The gradient, the tangent lines would be more and more steeper as you go from T1 to T2, right? Very good. So that means that the rate of the reaction is increasing. Okay, so very interesting. A little bit of a new thing that we haven't discussed. They say that changes in the graph in T1 and T2 are due to temperature changes within the reaction mixture. Is the reaction exothermic or endothermic? So we see that the gradient is increasing steeper, very much steeper, steeper, steeper as we go from T1 to T2. So that means the rate of reaction increasing. Okay, think of it like this. Endothermic, we would absorb heat. So the temperature would decrease. Exothermic would release heat, okay? So the temperature would increase. So what would result in the gradient being increased? Meaning, what would result in the, what do you call this thing? In the rate of reaction increasing, because the gradient increasing means rate of reaction has been increased. So which one of the following reactions would result in an increase in rate of reaction? Exothermic, where there's releasing heat, temperature increase, or endothermic, where there's absorption of heat, temperature decrease. What do you guys think? What would result in the rate of reaction increasing? The releasing of heat increase in temperature, exothermic, or the absorption of heat decrease in temperature, endothermic? What do you guys think? Anybody? Okay, I'll help you out here. So in this particular case, because the reaction rate increases, remember from the factors affecting rate of reaction, we learned that an increase in temperature would increase the rate of reaction. Here we go. When at high temperatures, the particles move around more, which increases the rate of reaction. So therefore, there'd need to be an increase in temperature in order for that reaction rate to have increased. And the increase in temperature would be caused by an exothermic reaction because it releases heat. So the correct answer here is an exothermic reaction. Okay, explain your answer by referring to the graph. Okay, listen carefully. I'll give you all the points that you need. The gradient of the graph between T1 and T2 increases. Therefore, the rate of reaction has increased. Okay, which means that temperature has increased. Okay, and therefore the reaction is exothermic. Okay, so exactly what I explained, just put in point 4. So the gradient of the graph is increasing from T1 to T2. Therefore, it means that the rate of reaction was increased and therefore the temperature has increased. And therefore is the reaction that was the reaction was exothermic. Okay, perfect. Right, I'll give you a memo answer for that as well. no stress. Let's look at 5.4. They tell us that the percentage purity of the sample is 82.5%. Calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius. Take the molar gas volume at 25 degrees Celsius as 24,000 centimeters cubed. Okay, when you see this question, there is no need to panic. It sounds fancier than it actually is. Okay, we are smart and we answer these fancy questions. So first, let's just revise quickly the formula for percentage purity. Percentage purity is equal to pure over impure. Your pure and your impure could be in mass or moles, as long as they both in mass or they both in moles. We have to compare apples with apples and oranges with oranges. Okay, so this is the formula for percentage purity. So remember, what is percentage purity? Percentage purity is calculating the purity of a certain substance, not a substance that is impure. So again, in this case, we had impure CaCO3. Just think of it as, okay, there's 15 grams of CaCO3 impure sample. Some of it is pure, some of it is dirt. That the dirt's not going to react. Okay, so they say calculate the value X. What is X? X is the final amount of gas produced in the particular equation. X is the final amount of gas produced in the particular equation. So we start off at 0 and X is the final amount. So now we given also the percentage 82.5. 82.5% is the percentage purity. So we take 82.5 and we sub it in there. Remember, with the percentage, or you can put it over 100. Now, the pure value, we don't know. The pure value, we don't know. That's what we want to calculate, how much pure was actually. So pure is the one that would actually react, okay? Because pure is the amount of pure CaCO3 that we're talking about, and that's the one that would actually react. Now, we sub this in, this is like backwards. Now, what is impure? We have it in terms of the mass. The reaction of 15 grams of impure sample, a lot of the times, the impure is always like given. Okay, so look out for that. So pure over 15 times 100. Sorry, this is not percent, because I'll tell you why. Because when you do this calculation and you already multiply it by 100, it gives you this answer here, 82.5. So you don't put the percent, so long as you put the times 100 here. Okay, so pure over 15 times 100. Okay, I hope you're okay with that. If you're confused about how I got this, please let me know. This again, this is for CaCO3. Now, what do we do? Just simple algebra manipulation. I'm going to take the 100 over as division. Here we're left with pure over 15. Take the 15 over as multiplication. 82.5 divided by 100 times 15. And this is going to give me the pure value. Again, I substituted this 15 grams, it's mass. So it's going to give me the pure value as a mass. Let me do this calculation. Here, I get the pure mass as 12.375 grams. Okay, so do you see that's the actual amount of CaCO3 that's used. So now we can use the equation, we can use molar ratio and stuff like that. Yeah, so also, excuse me, this tells you the percentage of it that's pure. So if 12,375 out of the 15 kg is pure, this 82.5% is telling you, oh, 82.5% of it is actually pure. So yes. Now, yeah, I could have also done another thing to say this. 82.5% of 15. That's also one way of understanding it. Okay, or you can sub it into the formula, it's also fine. Okay, so I have the pure mass. What do they want? Calculate the value X on the graph. So the value X on the graph is volume. Okay, so remember, what am I doing? Okay, I'm doing perfectly fine. So yes, the reason I use the reason I use percentage purity because this is my way into the chemical equation. I always want to find my way into the chemical equation so that I can do what? So that I can utilize the molar ratio, and the molar ratio I can just bounce between one to the next, just take the moles, either multiply it by 1, multiply it by 2, divide by 1, divide by 2, just depends on the molar ratio. Okay, so this has given me a way into the formula. So let me just take this formula with me. Okay, and what have I done here? I have calculated the pure mass of CaCO3. Remember, this guy is in excess, this HCl is in excess, so all of the CaCO3 will react, meaning all of the pure mass. So we know for sure that 12.375 grams of CaCO3 has reacted. So now what do I need to do? Always I want to convert it to moles using this formula. Small m over big M, which is equal to 12,375 divided by, if we consider the molar mass of CaCO3, it should be, is it 100? It is indeed 100. Someone confirm it for me. Okay, and then what we do now is we divide this by 100, move this, we get 0,12. Hectic. Okay, so yeah, we take this, divide it by 100, sorry about that, and we get this number in moles, okay? Jeez. Give me 1 second, sorry. Just give me 2 minutes and I'll be back shortly. Okay, sorry about that. I am back. Okay, cool. So yes, we are busy with this. So why could we now calculate the moles of something in the formula? Because this was an actual amount that was used. How do we know? Because it was the pure amount and we know it was the limiting, so all of it was used. Cool. So we have its moles. So what do we have? I just said it. We have its moles. We have its moles. Very good, very good. So now we can go here and say, very nice, very nice. We know that this is, and when it comes to chemistry, you want to keep like 5 decimal places. I mean, especially for like moles and stuff, you can round off at the end. Okay. So 1, 2, 3, 7, 5 moles. And now we use the molar ratio. So we can show us using the molar ratio by saying CaCO3 is to H2L, HCl is a 1:2 molar ratio. What is the molar ratio? It is the coefficient of the chemical substance. So if this is 0,12, 12375 moles, this will be, let's multiply that just by 2. This would be 0,2475 moles. Okay, that's the 1:2 molar ratio showing right there. So now, very nicely, we now have utilized the molar ratio to get the moles of this. This is where we want to be. No, I apologize. Sorry. We were supposed to work with CO2 because that's what they wanted. They say calculate the value of X on the graph, assuming that the gas collected at 25 degrees, take the molar gas volume, because they want this amount. Sorry. They want this amount X, which is the volume of CO2. So we want CO2. We have to work with CO2. Okay. Second. We have to work with CO2. Okay. So let me just look here. Yeah, sorry, we have to work with CO2 because they want the volume. And I'll show you the perfect formula that we use. So let's ignore this. Okay. So now we're going to say this is to CO2. Very nice. It's a 1:1. So we have the same moles. So now we can work with this guy. Okay. And we can work with this guy to do what? Which formula in particular? Remember, we need 2 things. In most formulas, there's 3 unknowns. So we need to know at least 2 things to calculate the third one. And that formula, because they give us molar volume, is going to be this formula. V over Vm, molar volume. Now at STP, that molar volume is like 22,4. But they can also give you specific ones at a specific temperature, and you use it. 24,000 centimeters cubed. We should convert that to decimeters cubed. And we divide it by 1,000, which gives us 24 decimeters cubed. Okay, these formulas require SI units, and the SI units for this is decimeters cubed. So volume is what we want to calculate. Moles is what we have. So we say 0,12375 is equal to the volume, which is what we want, divided by the molar volume, which is 24. When we do this calculation, we get an answer of 0,12375 times 24, 2,97. If you round it off, you might get a slightly different value, and they should be quite moderate, quite lenient when they're marking. Okay, you'll probably have a span of 0,05 maybe. So 0,05 above this, or 0,05 below it, or 0,03 above it, 0,03 below it. Because if you round it off here to like 4 decimal places, 3 decimal places, it should be fine. But that's why I say just always keep about 5 decimal places for these things, round off at the end. Okay, that's always the nicest option. Okay, IMO. Okay, so yeah, that's the final answer for this question. We calculated X, which is the volume produced, the final volume produced at the end. Again, remember, in the equation, We can only substitute and also only calculate values that are actually used and actually produced. This is a graph that shows measurement of what's actually produced of CO2. The graph don't lie. Okay, hope we understand and hope we're on the same page. If there's anything that's confusing about this, please do let me know. Let's move on. 5.5. What are these? Are these theory questions? They seem to be. How will the rate of reaction change if 15 grams of pure sample of CaCO3 reacts with the same HCl solution? Choose from increases, decreases, or remains the same. So instead of this being instead of this being 15 grams of impure sample, if we used 15 grams of a pure, if we used 15 grams of a pure substance, okay, if we used 15 grams of a pure substance, how would it change? Can I get any idea? Can I get a increases, decreases, remains the same, or not sure in the chat, please? Okay, Mr. MC says increase. Do you agree with him, Harry? Harry Maguire. Not sure. Okay, cool. So sometimes you may think, okay, it's a solid, right? So it might not affect it, but we increase the size of the solid essentially. So in this particular case, right, this is obviously they're asking what? They're asking one of the factors, okay? One of the factors, they're asking one of the factors, right? So in this particular case, we are increasing the solid, okay? So there's two ways you can think about it. We are mixing the solid with an aqueous solution, okay? So if we add more solid, so let's just say this is HCl, and we add a solid. Even if we add a block of the solid into this thing, right? If we compare adding this block compared to a slightly bigger block like this, okay? At the end of the day, right? Here, when we change to the red one, we are increasing the surface area of the reaction. So even if it's a block solid like that, or even if it's particles, 1, 2, 3, 4, 5, 6, 7, 8, 10. Just say there's 10 there. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so even whether it's a solid or whether it's particles, whether it's crushed up into like a powder or something, then in that particular case, we are increasing the exposed surface area to the HCl. So we are increasing surface area, which increases the rate of reaction. So just be careful. This is a solid, so we talk about surface area. If it was a gas or a liquid, we talk about concentration, increase in concentration, because now we're adding more per unit volume. But when it's a solid, we talk about surface area. Okay, so how will the reaction rate change if 15 grams of a pure sample of CaCO3 reacts? This would increase. Correct, Mr. Muhammad Kareem. It would increase. 5.6, use the collision theory to explain your answer to question 5.5. Okay, so collision theory. It would increase. Why? Because there are more CaCO3 particles exposed with a greater surface area, which results in more effective collisions per unit time. Okay, and just 2 marks. Okay, so just 2 marks essentially. So if it's just 2 marks, that's all we mentioned. If we go back to our factors quickly. So yeah, we mentioned the factor. We mentioned the factor, which is in this case, surface area. So we say there are more CaCO3 particles exposed with greater surface area. Okay. Then we say, okay, more particles have sufficient kinetic energy. That's only for temperature. We say more effective collisions per unit time, and then we'd obviously therefore say higher rate of reaction. But in this particular case, just for 2 marks, we just have to mention the 2. Obviously, by saying increases, we get that 1 mark. saying increases the rate of the reaction. Okay, again, I'll leave the memo answer for that. Okay, cool. So I hope that makes sense. Okay, we're gonna work till about 10 because we did start a little bit late. So we'll leave out this question. You guys can go ahead and attempt this question. Let's look at some graph calculation. Let's look at some graph questions. Okay, and this experiment question. Okay, so right here, learners use the reaction of sodium thiosulfate solution with dilute hydrochloric acid to investigate several factors that affect the rate of a chemical reaction. The balance equation for the reaction is Na2S2O3 aqueous plus 2HCl aqueous gives us 2 NaCl aqueous plus SO2 gas plus plus S sulfur, which is a solid, plus H2O, which is a liquid. Define rate of reaction. Again, there's many. The main one, which you should just learn and use, is a change in concentration of products or reactants per unit time. Let's look at the 3 investigations. The 3 investigations, 1, 2, and 3 are carried out. Investigation 1. The results obtained in investigation 1 are shown in the graph below. So we have concentration on the x-axis, and generally we have our in-depth independent variable on the x-axis, independent variable. Generally, we have this on the x-axis and the dependent on the y-axis. So if you're given a graph, that's how you can determine from the graph what's dependent and what's independent. Okay, cool. So the results obtained in investigation 1 are shown below. So concentration is being changed and reaction rate is being affected. So as you can see, we move from left to right, which means the concentration is increasing, and we also move from up to down. The graph moves up to down, so therefore it also means the reaction rate is increasing. So as the concentration increases, the rate of reaction increases. For this investigation, write down the dependent variable. Dependent variable generally in this section is always rate of reaction. 5.2.2, conclusion that can be drawn from the results. Now, very importantly, for the conclusion, we always want to say, as, this is a general answer, as the independent variable, and obviously we'll specify that, increases or decreases, okay, the dependent variable increases or decreases. Just depends whether there's a direct. So obviously, you're not going to say increases or decreases. You're going to choose the correct one for your, okay, for the particular example. So can you guys give me the answer for this question, please, using this guideline that I gave you? I'll zoom out in a second. Substitute basically independent variable with our actual independent variable, and dependent variable with our actual dependent variable, and increases, decreases with the particular example. So that's your conclusion. As the independent variable increases or decreases, the dependent variable increases or decreases. That's generally what we always do for the conclusion. Can someone tell me? Fill it in for our particular example and give me the answer, please. Please. No, look carefully. You're saying as reaction rate increases, the concentration increases. No. You are telling me as the dependent variable increases, the independent variable increases. Always the other way around. The independent variable. Oh, why does thing stop sharing? Yes, correct. The other way around. Okay, be careful. Okay, be careful. So in this particular case, it would be as the concentration increases, the reaction rate increases. Okay, look out for that. Just give me a second. I'm going to see the other class. Tell them to panic. Stop What is going on? Is this growth? Okay, perfect. Right. Now, cool. Okay, let's look at this. 5.3. The Maxwell-Boltzmann distribution curves A and B below represent the number of particles against kinetic energy for the reaction at two different temperatures. Okay, so yeah. Remember the area after line P, which represents something, are the particles that undergo effective collisions. Everything before that undergoes just collisions, okay? Not non-effective collisions, ineffective collisions. 5.3.1, it says, what does line P represent? Do we remember? Anyone? Does anyone remember? Answer or tell me, don't remember. No. What does line P represent? Awesome, very good. Activation energy. Okay, because it reaches the energy to become an effective collision. So it is activation energy. 5.3.2, which curve was obtained at a higher temperature? Let's see if we remember it. So even if you don't remember what the description for higher temperature in terms of the graph should look like, you can maybe try and look at the graph and see which of these graphs have more effective collisions, because the one with more effective collisions would be higher temperature. So which graph was obtained at a high temperature? A or B? What do you guys think? B, okay. Hari says B. Let's just go have a quick look back at our graphs and decide. So just firstly, when we increase the temperature, actually I should change this. This is increase, add. When we increase the temperature, the graph becomes more flattened. And we see the example here. So remember, all of these are increase temperature, increase concentration. We can see that the original one is this red one, right? Then when we increase, it flattens out and goes further. So now it adds so much more, all of that. So you are correct indeed. It is B. Okay, B was obtained at a higher temperature. Explain in terms of collision theory how an increase in temperature influences the rate of reaction. So let me give you a complete answer for that. Okay, this is a full 4-mark question. We have to mention 4 things. Explain in terms of collision theory how an increase in temperature influences the rate of reaction. So at higher temperatures, the particles have a higher kinetic energy, or they move faster. Okay, so remember, this is the first point here. Mention the factor, which is temperature, and you must actually mention like the definition or the description that I give you and say that it increases. Okay, so at a high temperature, at a high temperature, the particles have higher kinetic energy. Then we have to say that more particles have sufficient kinetic energy. Okay, more particles have enough or sufficient kinetic energy. If you want to mention extra, you can say sufficient kinetic energy equal to or greater than the activation energy. Then we can say that therefore there are more effective collisions per unit time, resulting in a higher rate of reaction or a faster rate of reaction, or the reaction rate increasing. So 4 marks. At a higher temperature, particles have higher kinetic energy. Okay, therefore more particles or more molecules have sufficient kinetic energy, if you want to add extra, equal to or greater than the activation energy. There are more effective collisions per unit time, resulting in the rate of reaction increasing 4 marks. Easy peasy, lemon squeezy. Let's look at this one. The potential energy diagrams X and Y below represent the reaction under 2 different conditions. Okay, Give a reason why curve Y differs from curve X. Can anyone remember this and give me an idea of why it differs, why Y differs from X? They say in one of the investigations, okay, sorry, so that's the next question. That's for percentage yield. You guys can go ahead and attempt that calculation after this. But what would be the difference between Y and X? Or give a reason why. Okay, so they're not asking you to say what's different about it. They're saying, why is it different? Okay, let's just go quickly to our graphs. So remember, these are our energy, potential energy viscosity of reaction graphs. And we have exothermic, for example, so more energy of reactants and products, endothermic, more energy of products and reactants, and so on. Okay, but very importantly, we have to look at for this question, we have to look at the effect of a catalyst. Okay, because what the catalyst does is it just decreases that activation energy. So that turning point on top is no longer so high. So it starts off at the same place for reactants, just doesn't go as high, and then it ends off at the same place as products. So that is catalyst that we need to be able to identify that what curve Y was obtained where a catalyst was added. So a catalyst was added, and therefore curve Y was obtained. So the difference is in curve Y, we used the catalyst. Okay, in curve X, we didn't. That's the difference.